Okay, one more example where we're checking whether a series is absolutely convergent, conditionally convergent, or divergent. So with this one, first thing I would want to do is rewrite this thing. I don't like looking at negative exponents. So I would write this as negative 1 to the n over e to the n squared. Okay, start at the highest level. Is it absolutely convergent? Absolutely convergent, question mark. So if we take the absolute value of the terms in this series, oops, that should be e to the n squared, then that's going to be, remember, absolute value of negative 1 to the n, that's just 1. E to the n squared is always a positive number, so the absolute value is just going to be that same expression, e to the n squared. Now we got to think about how we want to test that series. So it reminds me, I would say I'd like to compare that with 1 over e to the n. Because that, so could be written as 1 over e to the n. That's a geometric series. Geometric series where r is equal to 1 over e. E is about 2.7. So absolute value of r would be less than 1. So this is a convergent geometric series. 1 over e to the n, but not n squared. So we need to compare those. I believe direct comparison test will work here. Right, because if we compare 1 over e to the n squared with 1 over e to the n, this is going to be a much bigger denominator, right? A higher power. So a much higher power of e means a much larger denominator in this case, so a smaller fraction. So we've got this series here is smaller than a convergent geometric series. So when you have the larger series as convergent, that puts us a lid on the partial sums for that lower series. So that would mean that this series converges, which means that this original series here is absolutely convergent.